Good afternoon. Yeah, this will be a little bit different because it's really a bit of a life's journey, and if anybody thinks being a spin out of university could be a get-rich-quick scheme, you'll note that I started Artemis in 1994, so it has been a bit of a long journey, but a really very interesting one, and not one that I'm sorry to have undertaken. Before I get a start, I'll just link myself into Terry, who I've met on many occasions before, and the site he was showing you at Hunterston is in fact exactly where we're going to be putting the first Sea Angel prototype later this year, and so there is an interesting connection there. The slide doesn't show the Mitsubishi logo is very small, but at the bottom of the Sea Angel graphic. But in fact, Mitsubishi has invested a great deal in our technology and in the turbine that's going to demonstrate the technology, and I want to make sure that they're properly recognized. But also along this path, we got a lot of support from Carbon Trust and from DEC when we did various stages of test, which we'll to some degree touch on during the talk. Now, apologies to people who've seen this before, and you might be asking yourself why I'm talking about marine renewables, but it's basically to illustrate a point. And when I first came to Scotland in 1978, everybody and their brother had invented a wave power device, and in order to sell them to investors who were going to make a lot of money on wave power, the key principle was that you had to name it after something soft and furry, and maybe a little green. And it took me a little while to work out that if I got a tree of life, I could actually map all these devices onto the tree of life, and it would be pretty good correlation, and that's what I've done here. So you see that the secret to being a successful renewable developer is to think of something soft and furry, find its position on the tree of life, name your device after it, and you're done. Except the real problem is that whilst the public perception, the thing you're trying to sell to your investors is the outside of the thing, whether it's the salter duck or the aquamarine oyster or the whatever, inside it's got some rather unpalatable things. In this case, I've got a picture of a digestive system off the web, and that's it used to be the problem of Artemis before Mitsubishi bought us, was that trying to get investors interested in digestive systems was very, very difficult indeed. But it does, the problem hasn't gone away. The technology that we've been developing is necessary to making the soft, green, fuzzy thing work. And as unpalatable as that is, it's really a necessary point. And in fact, once you've got something that might work, you also need to test it, and you need to test it very, very comprehensively. So, in fact, my talk today is about going through that testing process. The other point of departure that I want to just establish is that when you go and you see most drive lines, and think you can be in a car with a manual gearbox, and you've got 4 speeds and whatever, and 6 speeds and at the tip of your fingers. These are fairly easy motion ratios to deal with. The car just has to go forward mostly, and the engine goes around fast, and the coupling of this motion ratio is not that challenging. In renewable energy, in almost every form, you've got a motion ratio that's very, very difficult to couple to the actual end point of the electrical delivery. So whether you've got waves or tidal or wind, you almost always have something moving relatively slowly with very high and irregular forces, and you've got to somehow transform that energy from that very difficult starting point into a constantly rotating shaft, hopefully with a relatively constant torque. And that's a very, very difficult thing to do. And in fact, that goes back to the very early days of wave power, when Stephen Salter actually recognized that in the Salter duck, he had to deal with both the hydrodynamics of how the thing behaved in the waves, but then he had to actually harness that energy and turn it into electrical generation. And in that process, he identified hydraulics as being the natural means of doing that when you have very difficult motion ratios. And Then he established that, in fact, conventional hydraulics was not good enough, and not good enough because it wasn't big enough, because it wasn't efficient enough, and because it wasn't controllable enough. So, in fact, Artemis was founded on the back of some work that's at least initially started at the University of Edinburgh, but then migrated off into the nascent Artemis in 1994, and has grown into the team that you see in the picture. So we're a multidisciplinary team. We have, I think, about 10 or 11 nationalities. We're based in Lone Head. We were at Edinburgh University until about 5 years ago when we outgrew our limited space. We're now up to 45 people, having started out as 2. And initially we worked on a licensing model where we licensed our technology to large companies that could get our technology into world markets. And that actually was a very interesting model, which very few people seem to have latched onto. But that kept us going and growing until we were bought by Mitsubishi in 2010, after which we've certainly given a lot of attention to their requirements of developing the world's largest wind turbine, and the first one with a very or the first large one with a hydraulic wind driveline. Just on the right of this slide, there's an interesting point I want to draw out. Artemis is mostly engineers, and we're mechanical, electronic, and simulation and software engineers, and we all live in the same room, and we work together in a very interactive way with very intense communication. And we view our projects as being a sort of continuous circular iteration as opposed to a linear process. And that means that we just hopefully get things to work better and better, and part of that process is testing, and that's kind of why I'm standing in front of you to talk about testing. I'm not going to go into great detail about our technology, but it's basically, we make hydraulic machines that we've developed from the ground up. We do a limited amount of manufacturing, but mostly we make design and make prototypes at our Lone Head facility. We make and have made machines that span about 4 orders of magnitude of torque. So from grass cutting machines up to the world's biggest wind turbines. And quite interestingly, the performance figures of all these machines look almost identical when you lay the performance graphs on top of each other. Our machines are very, very efficient, better than, equivalent to or better than electric machines of the same sort of scale. But they have some very useful advantages over other forms of power transmission like gearboxes and so on. I'll go into the specifics shortly. We cause the flow to come in and out of our pistons and cylinders with digitally actuated valves that we've designed ourselves. We consider that to be part of our treasure trove of intellectual property. And that gives us machines which have infinitely variable displacement. So they're controllable electronically with a very high bandwidth. They also work at a very high pressure, which gives us a very high power density. And the nature of hydraulics is that the components all load share, which means that unlike, say, a gearbox, where you've got a few gears that are doing all the work whilst the other teeth are on holiday, with hydraulics, everybody bears a certain amount of burden all the time. And that burden is capped because if the pressure gets too high, we can always vent the pressure and stop it from going beyond a certain amount, which limits the mechanical stress. And that gives us a very durable technology that's very robust against overload. And it means that we don't have to have massive safety factors. So that's the kind of stuff we're doing at Artemis. And I'm going to illustrate how that fits into a wind turbine very quickly. So that's we're looking at a nacelle of a conventional wind turbine with gearbox and power electronics. And basically what Artemis technology does is going to remove those 2 components. And some of you will know enough about wind turbines to know that those are perhaps some of the most problematic components from a durability and cost of OpEx point of view. And we're proposing just to remove them and replace that with a slightly different system, whereby we would, instead of having a gearbox, have a hydraulic pump and motor or motors driving synchronous generators. So this slide shows the rotor driving a hydraulic pump. It's running maybe at 15, 20 RPM. This is a 1.5 megawatt scale. We did quite a lot of work with Carbon Trust funding at 1.5 megawatt scale. And so we've got a pump, which is something called a ring cam pump. It's running at about 97% total efficiency. And that's sending fluid at a controllable rate into the two red things, which are hydraulic motors. And those are turning at synchronous speed, 1,500 RPM perhaps, driving generators. And you'll notice that there's two of them, and that's on purpose. That's because if you look at the load factor of most wind turbines, it's usually below 50%. So at any average time, probably one of those motors and the associated generator is shut off, and that means that the parasitic loss of those machines is not being borne by the efficiency of the parasitic cost of the machine, which improves overall efficiency. This is the actual thing made real, but we haven't put it up in a wind turbine. We built it in our lab. So I'll just go through this from left to right. We start with a 1.6 megawatt motor, and that's driving a wind turbine gearbox going backwards at about 100-to-1 ratio. So the output of that is, again, is wind turbine rotor speed. The darker blue machine is our pump. Just by contrast, that gearbox weighs 24 tons. Our pump weighs 7 tons. They don't have quite the same torque rating, but if our pump did, it would be about 9 tons. So we're about somewhere between a third and a half of the weight of a gearbox. The flow comes out of the pump. You can see 4 lines going along the floor, and those are going through flow meters and into the red machines, which are the hydraulic motors, and they're driving generators. And behind there, you'll see some white cabinets, and those are the regenerative active frequency inverter system that can regenerate power from the back to the front. And that's a 1.6 megawatt test rig that we built in Lone Head. It's active now, and it's been very good. We can do not only static testing, but also follow dynamic wind profiles, and it could also do tidal profiles or whatever else we wanted to do with it. The next shot is just a few background shots of the actual facility. So we can see the back of the pump. We can see the control cabin. The control cabin is kind of an interesting thing. Initially, we put all our dangerous hydraulic machines into containers to protect the test engineers. Now we put the test engineers into the containers because the test rigs have gotten too big. And on the right, we've got the 2 hydraulic motors. So this worked, and it worked so well that the directors of Mitsubishi Heavy Industries in Japan were convinced that we had the wherewithal to commit, or they had the wherewithal to commit this technology to the Hunterston Sea Angel. But not at 1.6 megawatt scale, at 7 megawatt scale. So, in fact, we had to do something else. We had to build a new facility, which we opened last year. We had a big launch with Vince Cable just about a year ago. We built a new building. We've got a very big crane. We've got a 4 megawatt double-ended motor. And we can put hydraulic machines on either end and have them regeneratively work through the from end to end. And this machine has roughly double the flow capacity than the previous small one. The reason it's 4 megawatts and not 7 megawatts is that, as you see, we have 2 generators, so each hydraulic motor only has to be about 3.5 megawatts in scale. So that's now been commissioned and is working, and we are now testing the components for the Sea Angel, which, as I speak, is being commissioned actually in Japan and will shortly be put on a ship to come back to Scotland. So that's the actual machine that we have in plan, and We like to keep thinking it's the world's largest, but it's obviously we've got some competition. Let's just hope ours is the best. I hadn't reckoned on what Terry was going to say, so it actually feeds in rather nicely to this slide. When I first came to Edinburgh, we were opening the wide tank facility, and again, we saw a picture of that in one of Terry's slides, or the successor to the wide tank. We built that at Edinburgh University to test the Salter duct, but then over time it tested about just everything else anybody could think of. And this is liable to happen with our test facility, and in showing you the two test facilities we built, which we call Windrig 1 and 2, the 1.6 megawatt and the 4 megawatt facilities. These are things that we're currently using, but there could easily be a time when they would be available for other people to perhaps rent from us. And certainly when we were developing the technology, we were asking around for dynamometer facilities, and they don't grow on trees. So maybe something for me to talk to Terry about afterwards. Right, so I think that draws my talk to an end, and better go back and start working on getting the Sea Angel to work. Thank you very much.
Thanks very much, Win. A couple of things I drew from that presentation. One of the things I think shows that marine energy and the wind sector may have more in common than we might imagine, and certainly through R&D and testing, we might draw some of those synergies out, and it'd be important for each industry to learn from each other. And again, Scotland clearly driving both for offshore wind and for marine energy may well show us the way how to do that. The other one is that acronym KISS, keep it simple, stupid. Taking two things, the gearbox and the power electronics, and replacing them with something cleverer, doing both things at once in a different and potentially more reliable way, less weight. If you're at the top of a 100-metre tower in 40 metres of water, you can't ignore that. That's what innovation's all about. And what did it do? Well, potentially it's going to introduce competition. That's one of the elements of cost reduction, is the competition in the marketplace. For sure, we've got the tried and tested gearbox, we've got permanent magnet generators, and now we have a third in the hydraulic drive. And competition between manufacturers for this market will drive down costs, simple as that. And then finally, I think the rewards for all that hard work, it isn't just the fact that that's coming back to Scotland. You look at Japan after Fukushima, the test and demonstration that they're putting in place, the Sea Angel will also be going up into Japan, so already an export market early on, so congratulations again. Are there any questions from the audience to Win about what he's developed with Artemis and Mitsubishi? Yes, a question from the middle. There's a mic coming down to you. If you could state your name and the company you're from before you ask the question.
Hello, my name is Alexandra Price, ex-Edinburgh University, and I just was wondering about the availability of the system compared to the gearbox and the power electronics that are being replaced.
Right. That's a good question. That's why we're doing it, and of course it's brand new, and I can't point at things that have been operating for a long time to give you a answer. But if you look at the industrial drive market, there's a company called Hägglunds, and Hägglunds make large industrial drives for particularly onerous duty, like rock crushers and sugar mills and so on. And those drives are not electric motors and gearboxes. Those are hydraulic drives with usually electric motors as an input. And those are the only thing that can cut it long term in these very arduous applications. And we would hope, given that a lot of our components are essentially analogous to what Hägglunds is using in their systems, that we should be able to achieve the same levels of reliability and durability in what is also an arduous situation. The other thing that I failed to mention, which was on my script and I just overlooked it, The Artemis equipment is completely, all the moving parts are very small and can be taken apart inside the nacelle and exchanged. So one of the big problems with an offshore wind turbine is the accessibility to change large components. So really our starting point for our design was to make sure that there were no large components that would require very heavy lifting devices to be brought on site in a very limited weather window. So basically everything can be fixed inside the nacelle. Might not be much fun, but you can certainly do it with a modest number of people in a modest time.
Any other questions from the floor? Time for one more if there's another burning question. Decent pause? No? Okay, so we'll move on to our last speaker.